So my name is Andreas TÜNNERMANN. I'm director of the Fraunhofer Institute of Applied Optics and Precision Engineering here in Jena, and I'm also chair for applied physics at the Friedrich Schiller University in Jena. Jena is the major capital of optics in Germany, so roughly 150 companies are working in optical technologies here in this area, and there are also several university but also non-university research institutions addressing topics in optics. We are undertaking and promoting applied research, especially here in this institute, with a focus on optics and optical technologies. Our customers are, for example, small and medium-sized companies, but also global players. And we are focusing on solutions based on light to overcome the big challenges of the future. For example, in the field of energy, communication, but also, for example, in the field of production technology. One prominent topic is, in fact, the development of novel camera systems to make cameras, for example, very flat to be used, for example, in mobile communication systems. And a topic we are addressing in the moment is that we pick up principles from the insect eyes. So we are developing bio-inspired optical systems. So this is a one aperture approach. This is an objective which is bio-inspired by the human eye. So which is basically the solution which can be found in any traditional camera system of today technology. And here we have an objective which is bio-inspired by the insect eyes. So it's a multi-aperture approach. Both systems deliver similar resolution if they are attached to a CMOS sensor. And as you can see in the direct comparison of these two devices, you can reduce the total length of the objective and, of course, in the consequence, the thickness of your mobile phone by a factor of 5 or even 1 order of magnitude, depending on the resolution, using this multi-aperture approach in comparison to the one aperture approach. In nature, roughly 27 different eye solutions have been developed, and the insect eyes, they have been developed for low weight, low volume, and low brain capacity. So basically these are the optimum sensor optics to be used, for example, for mobile communication systems.
My name is Andreas GEBHARDT and I'm responsible for the ultra-precision manufacturing at our institute. And one of the main topics in the field of ultra-precision manufacturing is producing metal mirrors and metal optics, especially for astronomy and space. So here you can see some examples of our work. So we are mainly making mirrors in soft materials like aluminum or even nickel phosphorus. And we did a couple of mirrors for different missions, for different instruments in the field of astronomy. One example is this, I would say, small example, which is called MERTIS. This is a special spectrometer for the observation of the Mercury. And we built a couple of models from this MERTIS spectrometer, the flight model as well, and the flight model will start next year to the very long journey to MERTIS. And hopefully we will get some results of this instrument in 2023. So this is made of diamond-turned aluminium mirrors with a layer of spotted gold for the reflection of the mirrors. And we produced the mirrors and we assembled the mirrors as well.
Hello everybody, my name is Jan Rothardt. I'm a postdoc at the Friedrich Schiller University and the Helmholtz Institute in Jena. And I am working in the field of high intensity and high average power lasers, especially focused on few cycle laser pulses. These pulses are extremely short events of optical oscillations, and they can be used for triggering ultra-fast or probing ultra-fast processes in nature, materials, and fundamental science. The laser system you have seen is a specially developed OPCPA system. OPCPA stands for optical parametric chirp pulse amplification, and it is capable of generating and amplifying pulses with a duration of less than 6 femtoseconds. And these pulses consist basically only of 2 optical cycles and can therefore be used to trigger events within a single half cycle of the laser field. For example, you can use these pulses for upconversion into the higher photon energy region. If you do high harmonic generation with such pulses, you can achieve the generation of a single event, which is an isolated attosecond pulse in the time domain. And this is, of course, very interesting for studying the most fastest processes in nature. We first developed the laser system, and then in the recent years, we were able to convert the infrared radiation to the XUV range to isolated attosecond pulses. And to do this in a controlled manner, it requires special precautions to the stability of the experiment. And now that we are able to generate these pulses, we are seeking for applications, and of course we will work together with other collaborators and scientists, for example, for studying ultra-fast magnetodynamics in materials or layers. One challenge for all of these type of experiments is you need to have enough photons to get a good signal-to-noise ratio in your measurements, and therefore we are also pushing the laser development towards higher average output powers. For the moment, this is already the most powerful few cycle laser system in the world in terms of average output power. It can deliver up to 22 watt of average output power, which is an order of magnitude higher than other laser systems. But we are, of course, pushing the limits towards even higher powers to have a reasonable amount of photons available for the experiments, good signal-to-noise ratio, and short integration times. This is especially needed if you want to do multidimensional studies, spatially and temporally resolved pump probe experiments, for example.
Well, there's a strong tradition, in fact, in Germany for a collaborative research approach between science and industry. Especially here in Jena, in optics industry, this is seen as a starting point for clusters, for research clusters, for collaborative research, public-private partnership models. This started more than 150 years ago in a collaboration between Zeiss and who was driving a small company in optics at that time, and a professor at the university. This was Abbe. He was chair of mathematics and astronomy. And Zeiss contacted Abbe, in fact, and asked him if he could develop solutions, mathematical programs in order to design, for example, novel microscopes. And due to this interaction, this tight link between the industry and the research institutes at the university at that time, this was the founding of the company Zeiss, the global player in optics. And we are working exactly in the tradition of these two people, I would say. So we picked up ideas in the field of optics and fine mechanics, for example, and combine this know-how and address with these technologies problems of our partners in industry.